before she starts. Dr. Ria Bhaumik is assistant professor with expertise in geotechnical and geoenvironmental engineering and geosynthetics. She have extensive experience working on multiple projects, slope stability of landfill components and natural and reinforced earth structures. She contributed and authored multiple peer-reviewed articles on slope stability studies and commended by professional societies for the same. Now I request Dr. Ria Bhaumik to make the presentation. Over to you, ma'am.
Thank you. Thank you for introducing me. Let me share my window. Okay, so today, when I was contacted by Sunil sir, he asked me to basically discuss about ground improvement. Now the issue is ground improvement is a full-fledged course, and because we are going to, cover very briefly about, it not in part in depth also, very brief points about most of the methods or the methods which will be useful to you, the engineers, the site engineers working on various dam projects. So that is why the title of this presentation is Brief Overview on Ground Improvement. As introduced by ma'am before, I am Dr. Ria Bhaumik. I am working as an assistant professor in Department of Civil Engineering, IIT Jammu. At the end of the presentation, we will try to address the questions that you may have as much as possible. In case if I miss some of the questions, or if you still have some, pertaining questions, you may write to me. My contact details are there at IIT Jammu website. With this, let's start. So why exactly do we need ground improvement? Now let's take a very basic problem that, all of us are civil engineers. I hope so. Now, as a civil engineer, if we ever come across with a problematic site to work with, now we will discuss very briefly what exactly do we mean by problematic site, but roughly it means that the soil in the site does not have the requirements which we need, requirements pertaining to the bearing capacity that is required, the settlement criteria that it has to meet, the permeability criteria, the compressibility criteria, all of these criteria. So if your soil does not meet these requirements, that means it is problematic to you as a civil engineer. So for example, if we have, a soil profile which looks like this, let me start, with my pen. Now, in this soil profile, you can see for the top 25 meters, it is a soft soil, and we all know soft soil, this very soft soil, they have basically an UCS value less than 25 kPa, which is a very low value to work with. So, and then this soft soil layer, these are underlaid with the silty sandy clay or the silty sand layers. So, as a civil engineer, the first, there are some options that you can work with. The first thing that you can work with is, if there is an option, if there is a choice available to you, and the choice should be based upon the cost optimization, right? Based upon the cost optimization, if you see like, relocating to a nearby site with a better soil profile is a cost optimum solution, you do that. If that option is not there, then you go for an adopting a deep foundation system. That means you try to reach the competent strata like the silty sand, or in fact silty sandy clay, based upon what exactly your lab data or the field data tells you about their bearing capacity or their properties. Other than that, you can go for a raft foundation system. Like, you can never go for an isolated foundation system in this kind of soil, right? So in that case, you go for a complete raft foundation system, again, which are a very costly option if you want to work within this zone only. The final approach or the final option that may be available to you is that you improve or modify the properties of soil as per your requirement, and that is what is known as the ground improvement. So we are discussing about problematic soil. So what exactly are the problematic soils that we may encounter, right? So there is an issue of the swelling and shrinking soil. I'm sure you must have encountered all of this kind of soils a lot while working on the site. So this swelling and shrinking kind of soil, like those soils mainly which has this highly plastic clay minerals like montmorillonite. So because of this high activity, the swelling and shrinking activity of monopolygonite that monopolygonite possesses, what happens, like when this kind of soil comes in contact with water, it can swell up to even up to 700% greater than its original volume. And when it swells up like that, the infrastructure overlying this kind of soil can undergo a lot of distresses. For example, we can see an example here. Due to this swelling phenomena, the pavement that was overlying this swelling kind of soil, it underwent distresses. The opposite happens in the summers, or when the water gets, water dries up. At that time, when it tries shrinking, because again this kind of it occupied a 700% increase in the volume. So when it's tried to shrink, there can be a lot of cracks in this kind of soil. So this can be a problematic soil to work with. Second is collapsible soil. So collapsible soil is that kind of soil, what happens if you come across a partially saturated, somewhat granular soil, which has certain plastic, some certain clay minerals as fines. Now, for example, a structure is shown here. There are certain particles and there is some cementation, some cohesion that is available. Now when there is in the the soil, when it is in partially saturated condition, there is a matrix suction pressure that is present in this soil matrix, like which we have learned about, that capillary phenomena that happens in a partially saturated soil. So there's a suction pressure that is present. Now, when this kind of soil comes in contact with water, more water, what happens? We know that the clay particles have this DDL, right? The double diffuse layer. Like these are charged particles which have certain requirement for the water. So once the charges, they get satisfied, the DDL gets absorbed, and the cementation, this bond will reduce. Moreover, when the water will come into contact with this, the matrix suction pressure that comes to zero. And because this matrix suction pressure comes to zero, the entire matrix collapses. Collapses in the sense it shrinks. The void, it collapses. And when it happens on a larger scale, huge amount of settlement can occur in this kind of soil. The kind of collapse that you can see here. So those are collapsible soil. Soft soil, I just told you all about, like very soft clays, which has UCS lesser than 25. Like very soft clays has UCS less than 25 kPa. Soft clays have UCS less than 50 kPa. And this kind of soils are tough to work with. You will mainly get this kind of soils in the coastal region, in the coastal belt. Organic soils like peats, they have a lot of biomass. And because of this trapped biomass, they are highly compressible. So again, that becomes a problematic soil. Loosely deposited sandy or gravelly soils, which are not compacted, which are loosely deposited, they have a lot of compressibility. When surcharge weight is there, it can undergo a lot of settlement until and unless it reaches an equilibrium position. Loosely deposited industrial waste material. Nowadays we are replacing a lot of natural materials with this industrial waste materials, because a lot of this stabilized or neutralized industrial waste, like which has proven to be not harmful to the environment, those have reuse potential as a infrastructure material. But this loosely
Excuse
deposited,
me.
yes.
Yeah, I think someone else one has shared the screen. So could you please reshare your screen?
What do you mean by someone else has shared?
Yes. So you have to reshare your screen, ma'am.
Okay, so
Someone reshared over to you.
okay. Is my screen visible now?
Yes, ma'am.
Yes, it is.
Okay,
Now
okay,
is
right. What you may do is like restrict this kind of controls to the general audience, like during a lecture is going on, right?
I would
So
request to the IT department kindly disallow all the participants and mute them as well till the time the session is going on.
Yes, yes, yes.
right. So let's continue our discussion. So yes, as I was telling, a lot of the use of this natural soil material is right now being replaced with this stabilized or neutralized industrial waste material. So again, when they are loosely deposited, it can be a problematic soil. So you need to find out the solutions to work with this kind of material also. So that's establishing why exactly do we need the ground improvement. Now let's look into what exactly is ground improvement. So ground improvement is a very broad category. Like there can be, tens and hundreds of methodologies that can be used. And why there are so many methodologies? Because the need of an, the need as to for you as a civil engineer, that can vary based upon what kind of structure is going to come up. The ground improvement methodology also depends upon what kind of soil are you going to work with, right? So that means exactly which kind of properties do you need to improve in your soil. So based upon this criteria, the ground improvement methodologies, they also differ. But overall, it refers to improve, like whenever you work with a soil which in its natural state do not possess the required properties that you require as a civil engineer, whenever you want to modify those, you need certain methodologies. And the most important thing is this improvement needs to be done on site. It does not mean that, there can be lab based or plant based mixing modification that will happen and you can bring it to site and install. Mostly that is not how this methodologies work, because you're working on a large scale. So this has to be carried out in situ. Now, if why exactly do we need this ground improvement? As we we had as we just discussed, you need to increase the bearing capacity of the soil. You need to reduce the amount of settlement that your soil can undergo. Not only the amount of settlement, but the time in which the settlement can undergo. For example, in clay soils. So clay soils, it's not a freely draining soil, right? So the water, it takes a lot of time for the water to come out. So that means it takes a lot of time for the settlement to happen, for the consolidation to happen. So if you want to accelerate that, in that case, ground improvement helps. If you want to accelerate the drainage in your soil, ground improvement helps. If you want to increase the capacity of your material to retard seepage, the kind of material that we use in dam core or for cutoff material, for those kind of material, if you want to increase the seepage is retardation capacity, ground improvement helps. Also, eliminate the possibility of liquefaction. We all know what exactly is liquefaction. So if you have a fine grained sandy soil that is saturated, that is in saturated condition, and such kind of soil when under earthquake loading, earthquake loadings are very short time loadings but very high impact loadings. So impact is high, the loading is high, but the time is short. So under such high loading, what happens? The entire load, at the moment when the load is induced, the entire load is first taken by the water. That we all know, right, from our understanding of geotechnical engineering, from soil mechanics. But with time, that load gets transferred to the soil grains. But because this earthquake is such a short span loading, there is not enough time for the stresses to get transferred from the pore pressure to the nearby grades. And that is why the effective stresses, those are present, it becomes zero, and the soil entirely starts behaving as a fluid. So you have a solid soil matrix. At under earthquake loading, it starts behaving as a liquid. That's liquefaction. And if you want to eliminate the possibility of that, there again ground improvement helps. It also helps in increasing the stability of your slopes, natural slopes, man-made slopes, open cuts, vertical cuts, openings. So it can be custom made, tailored, it can be tailored as per the requirement of the site, requirement of the project. Now, if you look into how exactly these methodologies can be classified, So first we have the mechanical modification. Mechanical modification means we are simply trying to improve the mechanical properties of the soil. Mechanical properties in the sense, suppose density of the soil, reducing the compressibility of the soil. So we are not exactly, introducing a new material simply by densifying your loosely deposited granular material, your soil will start improving, behaving in a better way. So those methodologies wherein you are improving the properties without including any external material by improving the mechanical properties of your soil, those are mechanical modification. Hydraulic modification, wherein you are changing the hydraulic properties of your soil. For example, you are accelerating the drainage, accelerating the consolidation. That's hydraulic modification. Physical and chemical modification is when you are modifying the soil by changing its structure, the basic structure of the soil, by adding some extra component. For example, for soft soil, we can use lime treatment. So what exactly lime treatment does? It acts with the clay kind of material. It improves its bearing property. It increases its cementation property. You can use cement or bentonite with, with sandy kind of soil. So you are basically changing the soil structure, the soil matrix. So by adding some extra component. So that's a physical and chemical modification. Inclusions and confinements means you are using an artificial material. So in physical and chemical modification, you are using some external chemical components to change the structure. In inclusions, you are using an artificial material to improve the mechanical properties of the soil. For example, geosynthetics. I hope you all are aware about geosynthetics. So geosynthetics can be used along with soil for increasing as a reinforcement, or increasing its, for increasing its strength properties, for accelerating drainage, for confinement purposes. So these are inclusion of all artificial materials. And then the final classification can be, combination of the above. For example, stone columns. So stone columns can be both mechanical and hydraulic modification. Mechanical because you're replacing a part of the soil with better kind of material, but stone column also acts as a drainage path. So it's improving the drainage criteria, drainage property of the soil. It's improving the consolidation, accelerating the consolidation. So those are the combination for work. Now let's look into the exact ground improvement methodologies. So further, like we just classified these methodologies. Now let's look into how exactly this can be used. So here again, we can have three categories of this ground improvement methodologies. For example, first is reinforcement. So reinforcement, basically what you are doing, you are reinforcing your weak or problematic material. So you have a field with soft soil. You want to reinforce it. So one way is to use this Vibro columns, which are also popularly known as stone columns. So what you are doing there, you are replacing around 25 to 30% of your soft soil with stronger soil. We are reinforcing your weak material. Soil nails, soil anchors. Those are again reinforcement measures. Geosynthetics reinforcement measures. Adding fibers to your soil to increase the tensile strength of your material, to reduce the permeability of your material. That's a reinforcing ground improvement methodology. Biotechnical measures. Biotechnical measures like you are planting this, specific grasses, specific shrubs, which has longer root reach, longer root length to stop the erosion. to stop the gully erosion or any kind of piping. So those are biotechnical measures. In this today, in our discussion, we'll mainly look into the Vibro columns. Coming to the improvement. So in reinforcement, you are introducing an external material, or you are kind of replacing some part of your problematic soil to improve the property. In improvement kind of methodology, you are not exactly introducing any external or additional material. Herein, you are introducing an external stress or external force so that the properties of your soft soil can be improved. For example, surface compaction or deep compaction. You are subjecting your soil material to external stresses, dynamic stresses or static stresses, so that your soil can get densified. And it is intuitive that if you have a denser soil, the compressibility of your soil will be low. The settlements will be low, the bearing capacity will be high, the strength will be high. So you're not introducing any external material inside your soil, you're simply subjecting it to external loading or stresses. So in our discussion today, we will also look into the surface and the dynamic compaction. In treatment, again, it pertains to, kind of changing the structure of your soil. So for example, adding some admixtures or additives, which can improve the cementation, which can, improve the cohesion, which can reduce the permeability. So that's treating your soil. Same with dewatering, thermal treatment. There are some biotechnical measures, introducing some bacteria and algae in your soil to improve the clogging or improve the cementation. So you're treating your soil again with some external measures. Now look into, let's look into each of this. Now coming to the first ground improvement technique, that is surface compaction. So before going to the surface compaction, let's have a basic just discussion about the compaction. We all are aware about it. We use it very frequently at site, right? Just to revise our entire idea about compaction. So compaction is basically what you're doing. You are densifying your soil to achieve the densest possible state by reducing the air voids. We are all used to with this graph, wherein we get this V kind of curve, right? This peak value, it gives us the OMC value, optimum moisture content, corresponding to which we get the maximum dry density. And all of this are under a certain compactive effort. We also understood why exactly this densest possible state is achieved. Specifically, if we look from the structure of clay, we understand that when clay is on the dry side of the optimum, which is this one, right? When the clay is on the dry side of the optimum, it has a flocculated structure. By adding more and more water, we are reducing this flocculated structure to the dispersed kind of, like flocculated is this kind of structure and dispersed is this kind of structure. And this kind of clay structure is mainly found in the wet side of the optimum. This is the optimum line, this is the dry side, this is the wet side. In here we get this kind of clay structure, in here we get this kind of dispersed clay structure. We all have a basic idea of this. Now let's see how exactly this can be manipulated, how exactly this can be changed with varying parameters. The first parameter that can change your OMC graph is the compaction energy. So that is why it is always necessary to mention the OMC graph that you have obtained in the lab. What was the compaction energy that you have imparted? So for the same amount, for the same kind of soil, this is the OMC curve under standard Proctor, while this is the OMC curve under modified Proctor. So first, we know that based upon the compaction energy, the OMC graph can be changed. Next, another thing that you will notice is that if you compare, the dry side of your curve. So this is our curve 1, this is our curve 2 for the same soil, just increase in compaction energy. Now, when you are compacting your soil in the dry side of the optimum with a higher compaction energy, you will see that the increase in the dry density is quite high. But on the wet side of the optimum, this increase is quite low. So that means if you are working on the dry side, just increase in the compaction energy will create a huge jump in the dry density. That's not the case in wet side. Again, this mainly comes back to the entire clay structure. What happens? Because on the dry side, you have a flocculated structure, right? Now, this flocculated structure can be changed to flocculated dispersed structure under higher compaction energy. So, this kind of structure can come into a more flatter dispersed, not exactly dispersed, but a more flatter dispersed. So as an all, when it tries coming to this kind of flatter structure, the density that it achieves, that also starts becoming greater. But in the wet side of the optimum, we know that the clay has this double diffuse layer. And this double diffuse layer, it actually repels any further compaction. And that is why even with increase in the compaction energy, you won't achieve much higher dry density. So it is always recommended that to work on the drier side rather than on the wetter side. Yeah, that's what I have discussed here. You can see like just at the, drier side, how exactly the jump in the dry density happens, but that's not the case in the wetter side. The compaction in this OMC graph also depends upon the kind of soil that you're using. So we all know that, OMC curve is not always, you cannot always get an OMC curve for a completely highly plastic clay or, a completely granular material. When you have a mixed kind of soil, then only this OMC graph is very prominent. The way you can see here, for soil type 1 to 6, you get a very prominent OMC curve, wherein you can see all mixed kind of soil. But the moment you start coming to the heavy clay, so it's a highly plastic clay and it behaves abruptly, very dynamically when it has come under contact with water. For the poorly graded sand, we know that compaction energy is exactly not the best way to densify sand. It works the best under vibratory stresses. So that is why even for completely granular material, you won't exactly get an OMC curve, a very prominent OMC curve. Herein, another thing is it is very important for you, like the OMC curve that you are getting in the lab, and you will see the OMC curve or the the compaction energy that you will get in field, they exactly won't match. Because the field compaction energy and the laboratory compaction energy, they will be different. They can be different. And that is why when you are doing a field control, you always have to look into the relative compaction, that is RC value. Like what was the maximum density that you could achieve, maximum dry density that you could achieve at field to maximum dry density that you could achieve at lab. That's the difference. And that helps you to understand. So RC value of 90 and above is like extremely good construction practice. That shows that the compaction energy that you have imparted in the field is somewhat similar to the lab compaction energy. Now, I was telling that why exactly we go for this compaction, because it is intuitive, we can understand, we can visualize, The denser the soil, it has a better bearing capacity, better strength. But it also influences other properties. For example, permeability. Now, again herein, if you increase the water content, like you have a soil which is compacted at the drier side of the optimum. Like drier side means this is your OMC, right? So this is the drier side. Now, if your soil is somewhere compacted with this kind of water content. Now, if you further, try to saturate, if you further increase the water content of this soil under the same, same packing density, the permeability that you will see is that it has increased. There is a slight increase. Sorry, I told the letter. So if you are working on the drier side of the optimum, the permeability is lesser, while on the wetter side of the optimum, the permeability is somewhat greater. And this again, comes back to the change in the clay structure. Coming to the next property, how exactly the compressibility of your material changes. Now, here it's not only about the wet side and the dry side, it's also about the stresses that you are imparting. Stresses means after your compacted field has been laid, what kind of stresses it gets induced. So for suppose after your field is created, after your field is constructed, after that the stresses which gets induced are low in magnitude. Under this kind of low stresses, the wet compacted side, they are actually great, like more compressible than the dry compacted side. Why is that? Because I was telling you, right? In the dry compacted side, changing this flocculated structure of the clay just by external, just by adding some external stress is not easy. And that is why the compressibility is less. But changing the structure of the clay when it is already on the wet side, that is much easier. So under low stresses, the drier side of the soil, they will be less compressible, but the wetter side of the soil will be more compressible. But when the stresses are high, the reverse happens. So when the stresses are high, under high compacted stresses, this kind of structure can change marvelously. You have a completely flocculated structure which can change to a dispersed structure. Because the structure is completely changing, that is why the compressibility is high. But that's not the case with the wet side, because in the wet side, you have a mix of dispersed or flocculated dispersed, a combination of those. Like this is a flocculated dispersed structure. This is a dispersed structure. So under dispersed structure, compacting them, increasing their dry density is tough. That is why the compressibility is low. So these are all to make you understand how exactly, if you exactly don't work with the OMC, if you work on the drier side and if you work on the wetter side, how exactly the soil properties changes, the other soil properties, like the permeability, like the compressibility. Again, how exactly the strength is governed. Now, for example, right now you will see the graphs for 6 different kind of soil. The 6 different kind of soil basically refers to various degrees of this clay structure. So for the soil 1, it has mainly random structure, or what we have just told as flocculated structure. This structure changes to flocculated dispersed and finally to dispersed as it moves from sample 1 to sample 5. Now, the more flocculated your structure will be, the greater it will have, it will give you a better stress strain curve. It will show you a higher strength value, as you can see here. The more randomly oriented your clay structure is, it will give you a better stress strain curve. Higher stiffness also. As your structure changes to dispersed, not only the peak changes, but the stiffness also changes. So basically that means whenever you are working with a soil on the drier side of the optimum, it gives you a more rigid response. So that was about how exactly the soil behaves under this compaction energy, and when you are working with the dry and the wet side. Now let's look into the various compaction techniques. So because we are talking about the surface compaction, right? So surface compaction means we can mainly work up to maximum 60 centimeter to 1 meter. Now the best way to densify or compact this coarse grained soils is using this vibration motion. So that's what you can see here. For the coarse grained soil, all of the techniques, they basically form the basis of vibration. While the fine grained soil like clays or silty clay or clay silt, they mainly take help of kneading action. Kneading action is somewhat the way we knead the dough, the flour, the atta. So that is the kneading action. So that kind of compaction action is best for fine grained soil. How exactly that is imparted, I think many of you must be aware about how exactly this kneading action is imparted for clay soils. So these are the various tools, widely popular tools that are used. So herein you can see this vibrating plate, vibrating rammers, and the stamping rollers. These are primarily used for granular kind of soil. Then you have this shift foot roller, which creates the kneading action that is required in the clay, which are mainly used for the clay kind of soil. Let's look into each of this in further details. So the first kind of compaction equipment that came into picture was a smooth wheel roller drum. This is still being used, but this is presently mainly used for compacting this asphalt layer, not exactly for the soil compaction. They're not very effective. So they have 100% coverage area in the sense like what exactly is the contact of this roller with the soil. So they have 100% coverage area, but the contact pressures are not high, it's very low, and that is why its effectiveness is low. Like its reach below the bottom of the surface layer, that is low. And the compactive effort is completely via static weight. There is no other compaction, like there is no vibratory action, there is no kneading action, simple static weight action, that's all. In pneumatic roller type, like basically these are rubber tire, wherein there is in a single axle there are 4 to 5 rubber tires which are attached, and over this a certain weight is applied to it. So because of this, it has a 80% coverage, relatively higher contact pressure than a smooth drum roller, and it can be used for both fine grained and granular kind of soil, because it has both static weight and the kneading compaction components. Shift foot roller, these are primarily used for the clay soils only. It has only 8 to 12% coverage, but the contact pressure is very high because you can see the spikes which creates the kneading action. So as this surface area is low, the contact pressure is quite high. Tamping foot roller, again, it has this kind of pad footing. So these protrusions, they are not exactly protruded like the shift foot roller, but it has protrusions. So again, it creates a kneading action. So again, it is suited for fine grained soil or the mix of fine grained and coarse grained soil. The mesh or the grid pattern roller, like you can see the pattern that is present in the instrument. So this has a vibrating component that is present in the wheel. So it's a weight component, a static weight component, a vibratory component that is present there, and because of the structure of this, it can create a crushing action also. So this kind of mesh or grid pattern roller, they are mainly used for this fragmented rock. So if you have to smoothen this kind of fragmented rock bed, this mesh roller, they are being used. And their contact pressures are also quite high, between 1400 to 6200 kPa. Then you have a vibrating drum roller. So we have seen this smooth drum roller. In there itself, you just get a vibrating component installed inside this wheel. So that's create the vibrating action. So it makes the smooth drum roller more efficient by creating a vibration component. So again, these are suitable for granular soils. This chart here, it shows the applicability of various this equipments, this compaction equipments for each kind of soil. So for a purely rock or soil to rock kind of strata, the grid kind of compactor, they are very well suited. And the grid kind of compactor, we have seen the compactive effort is a combination of static weight, kneading plus vibration. For a purely clay soil, ship's foot roller is best, as we have seen. For a sandy soil, the vibratory rollers are very well suited. In fact, the smooth steel drums also, but not that efficient. For a mix of this fine grained and coarse grained soil, like clays and sands, the pneumatic, the multi-tired pneumatic, or the tampic foot roller, these are used. Now let's rush back because we don't have much time. Okay, anyway, now two other things that I wanted to cover regarding this surface compaction is, for each of this machine, other than which kind of compaction energy they are imparting, it also, like the other operational aspects which an engineer should take care of are, first of all, the vibrating frequency, which refers to, like, any machine has a range of frequency that it can work with. Now for the particular soil that you're working with, which frequency will give you the desired density, you have to find out. So your operational frequency is the first parameter that needs to be defined. The second is, what is the depth of lift? Lift means if you require a 1 meter compacted soil layer, so it is not advisable to compact this entire 1 meter layer at a one go. The reason being, see, this is a single lift compacted layer. Now this dashed line here refers to the relative density of the soil before compaction. So the relative density of soil before compaction across the depth of your lift was constant. After you have given some passes in a single lift, after you have applied the compaction force, the relative density will improve, but it's not linear. It has this kind of parabolic shape. So that means as you go down, the relative density of your soil approaches the relative density of the soil that was present before compaction. And that is why, to make it more effective, you need these lifts so that you get a properly compacted soil at around across the entire depth. So you have to decide how many lifts are needed, and that should be mentioned. Again, number of passes are also important. So herein that relation is shown for different kind of material and different kind of compaction energy also. So how exactly your dry density increases with number of passes, you have to see at what number of passes you are achieving the dry density. Based on that, you have to decide. Now coming to the deep compaction, that was surface compaction. Right now let's look into how exactly, if you want to compact larger depths greater than 1 meter up to maybe 15 meter, 10 to 15 meter, what are the ways? Now before we go into the deep compaction, one basic thing that we have to understand is the response of sands to external stress and the response of clays to the external stress, those are different, right? Because water sands, they are freely draining, they are highly permeable, and the particles, they are electrically neutral. There is no intercharges which are present. There is no, particle to particle interaction which are present. And for this reason, these particles can get rearranged under compaction energy very quickly. So the densification can occur under no time. So if you have this kind of, sand to sand particles, under simple application of energy, they can come together very easily. You can compact and densify it very easily. But that's not the same for the clay, because clays are not free draining. They have very low permeability, and they are electrically charged. So there is this interparticle forces. And because of these reasons, because of these reasons, they resist this particle rearrangement. And that is why the way they react to this external stresses, that is different. And because their response is different, ways to improve them are also different. We'll look into it. Now coming to the first deep compaction method, that is a dynamic compaction. So dynamic compaction, basically the idea is what you're doing, a very heavy weight, somewhere ranging between 6 to 170 ton, it is dropped constantly from a height of 10 to 40 meters in a bed of granular soil. So because it is dropped, so there is weight and there is drop height, right? So it's creating an impact energy. This impact energy again will have surface waves, right? And the shear waves and the compressional waves. So under this action of waves, the soil below it, it gets compacted. That's the basic fundamental basis of dynamic compaction. What exactly is the degree of densification? That depends upon what exactly is the energy that you're imparting, what is the kind of soil that you have, the properties of the soil. Now, how much is the depth of influence? Like, you are imparting this energy. Under this energy, how much depth can you influence? You can easily find out from this relation. It's a very straightforward relation where the depth of influence is half of root over of falling weight multiplied by the height. Weight is in tons, height is in meters. So from there, you can roughly find out the depth of influence. Because based upon this depth of influence, you also have to decide this grid spacing. Like where exactly, this next passes will be imparted. So how deep you want to reach, that will govern your center to center spacing. So if you want to reach a greater depth, your center to center spacing needs to be higher, because based upon the load distribution mode. But if you want to reach the lower sections, lower depths, your center to center spacing needs to be lower. So based upon how much depth you want to cover, your grid spacing needs to be defined. Now, once this, once this heavy weight, it comes down, it compacts, but it also creates a crater. So then once these craters are created, all of this are then backfilled with either local soil material or any other granular material. So that's the basic fundamental of the dynamic compaction. Herein I wanted to, this is a typical graph which shows the effect of the dynamic compaction across the depth of a layer. So what you can see here at various depths, the N value, these are all N values. Sorry, I did not mention that. These are all SPTN values. So N values before the impact and N values after the, compaction after the impact, those are measured. What you will say up to, a depth of 10 meter, the improvement is significant. But after, a depth of 10 to 12 meters, the improvement is less. So that shows what exactly is the depth of influence of your entire dynamic compaction design. And it can be used for, saturated, partially unsaturated, sandy silts, clay silts, sands, for those kind of soil. Let's go to the vibratory compaction. So right now we have seen, like, we are simply, imparting a falling weight energy onto the field. In vibratory compaction, what exactly is being done? This instrument, this part of this equipment is known as a Vibro float. So Vibro float can be used both in sands and clays, but how exactly they are being used and what exactly is being done after they are being used, that changes. So in sands, what happens is, like, this Vibro float, it goes down. So the way it works is somewhat similar to this needle vibrator that works in while compacting this concrete mix. The only difference is a needle vibrator, when you start mixing it for the concrete, it goes down via the vibratory action and via its self weight. For the Vibro float, just the vibratory action and the self weight is not sufficient. So that's why an additional component of this water jet is also needed. So there's water jet, there's weight of this material, weight of your Vibro float, and the vibration. So under this three components, it starts cutting it, it starts going down. Now in granular soil, what happens? Under this forces, the nearby sand, it starts getting compacted. And while the nearby sand starts getting compacted, there is a cavity which gets generated here. That cavity which gets generated, that gets backfilled with granular material. And you get a complete granular column created inside. So that's the use of Vibro flotation in sands. In clays, what happens here, because the clay exactly do not get rearranged the way sands do, right? So in clays also a cavity do get created, but here again this cavity gets backfilled as a stone column as via this granular materials, and you get what are known as granular columns or stone columns. So here you are not exactly packing the material, but you are replacing the material with a more competent material like sands or gravels. So you are replacing around 25 to 33% of your material with solid columns, solid materials. So that's Vibro flotation in clays. Now, when the content that I had to cover was shared with me, it also included the emerging trends in ground improvement. Like what presently are the hot topics in ground improvement, because the other methods, they are being used, they are in practice for 2 to 3 decades. So presently a lot of focus is there on the use of biotechnical measures. The biotechnical measures, I was just discussing the use of this bacterial treatment specifically to create a soil cementation and soil clogging. Soil cementation to increase the strength, or soil clogging to reduce the permeability of the material. But yes, this kind of measures has some lacuna, and it is still, people are researching. So it's a hot topic. These are an emerging trend, the use of, this bacteria and the algae in soil to improve their properties. The next is this use of this stabilized or, inert industrial waste materials as a replacement to the normal soil material. So the use can simply not be for the, just as a replacement material, but some of the industrial waste materials can also be used to stabilize or as, as an additive or an admixture. Second, these are some of the, other ground improvement methods which are right now being covered. So that's all I wanted to cover in today's lecture, and let's hope, with all of this, here in this slide, you can see all of the United Nations Sustainable Development Goals. And we civil engineers have a lot to contribute to this Sustainable Development Goals. And let's hope with our efforts, we continue to do so. So that's all. Thank you so much for being a patient audience.
Thank you, Dr. Ria Bhomik, for making an excellent and detailed presentation. Now, may I request to the participants, if they have any questions, they may ask. IT, can you please allow the participants to unmute themselves if they want to ask any question? Yeah, please. The participants may ask the questions. I believe we don't have any question right now. If still participants have any questions, they may write to us directly. We will arrange the answer from the speaker and get back to you over the email.
Right. Thank you for that. And you can also write to me also over my official email. That's also you can do. And I would like to connect with all of you. I would like to understand, listen to your field experiences. So thank you. Thank you so much.
Yes, definitely. Thank you, Dr. Ria Bhomik, for sparing your valuable time for conducting this session. Thank you so much.
Thank you.
Ladies and gentlemen, now may I invite today's next resource speaker, Dr. G.V. Ramanna, for making the presentation. Can I request the IT team, can you please confirm the speaker is available online? Dr. G.V. Ramanna.
I think no, madam.
I just need a break for a while. Let me check, and I'm just pausing this session for a while, please. Kindly bear with me.
What is about next lecture?
We are getting in touch with Dr. G.V. Ramanna, our next resource speaker. Kindly bear till the time. Thank you. Is Dr. G.V. Ramanna is available?
Yes, please.
Okay, we are just waiting for you, sir. So
Yep,
now I request Dr. G.V. Ramanna for making the presentation. Let me introduce briefly about the speaker. Dr. G.V. Ramanna is currently the... Yes, sir.
Hello.
Hello.
Hello. Hello. Yes, please. Hello. How are you doing? Hello.
Can I request to the IT team kindly mute all the participants? Hello. We will address the question only at the end of the session.
Hello, madam. I speaking from Jabalpur, sir, madam. I have a question.
Question to Dr. Ria Bhomik.
No, madam. Question for you. For you.
Question
So
for me, yeah, please.
I have question to you, madam.
Yes.
To achieve the compaction up to a desired extent by rolling. By means of rubber tire
Sir, it's
roller.
a technical question. I would request you, I'm not the concerned person. You should ask this question to the speaker. Now you may write to us through the email. We will get back to you with the respective answer. Now I request to the IT team, kindly mute all the participants, please. Dr. G.V. Ramanna is currently the head of the Department of Civil Engineering, IIT Delhi. His area of interest are geotechnical earthquake engineering, ground improvement, and geoenvironmental engineering. He has guided 19 PhD theses, 1 MS thesis, and 60 MTech theses, primarily in the area of geotechnical geoenvironmental engineering, documented the research efforts in various reputed journals and conferences. He had been principal investigator for several research projects. He is actively associated and contributed to the multiple dam projects in India and abroad. He has been a member of several panel of expert committee members associated with over 100 consultancy projects dealing with specification of geotechnical investigations, recommendation of bearing capacity of shallow and deep foundations, soil structure interaction of high-rise buildings, design of deep excavations, vibration assessments and isolation, and mitigation testing of geosynthetics, design of ash ponds and landfills and slope instability assessments and remedial measures. He also peer reviews design of RE walls and RE slopes. He actively disseminates geotechnical expertise through invited lecture at short-term courses, training programs for graduate engineering and at professional organization. Now I request Dr. G.V. Ramanna to make the presentation, please. Over to you, sir.
Thank you, ma'am. It was not a short introduction, very long. And are you able to see the screen, ma'am?
Yes, but the presentation is not visible.
Now?
Now it is visible.
Okay. Thank you, everyone, and good evening. You just listened to Dr. Ria Bhaumek on ground improvement. So this is a case study I'm going to discuss about on densification of loose sand below a large ECRF dam. Earth-cum Rockfill Dam is being constructed now on River Godavari. So Central Water Commission is involved in it, and it is being constructed by Mega Engineering Company. If you just giving you the introduction, this river, Godavari River from Nasik, and it goes and merges in Kakinada. The dam site is close to Bay of Bengal. It is about 60 kilometers away. This is the satellite image. One second. This is where the dam is being proposed. It is about 2 to 2.5 kilometers in length. The height is not a lot. It is about 40 to 45 meters. It keeps varying. The river flow is in this direction. And just to show you, I superimposed the AutoCAD diagram to show you that this is the dam, and then you have spillway here. This is your spill channel, and the water is flowing in this direction. When they are constructing, the primary thing is we would like to avoid liquefaction. And as the work started to progress, geotechnical investigations were carried out, and we started to encounter different kind of failures. The dam is basically divided into gap 1, gap 2, and gap 3 for the purpose of nomenclature. This is your dam section. The gap 1 dam is between 2 hillocks, and the length is about more than half a kilometer. It is about half a kilometer. Gap 2 which is the main portion of the dam covering across the width, is about 1.75 kilometers. The gap 3 is only about 100 meters, 150 meters or so. And there was a debate on trying to make a earth dam or a concrete gravity dam. And if you look at the Polavaram Dam site right now, the Google image would look something like that. The dam is under construction. The dam is under construction. This is the upstream coffer dam that was built. This is your downstream coffer dam. This is your spillway. And construction is going on. The main dam has not been started yet. This is how the river flows. This is your upstream coffer dam, downstream coffer dam. This is your spillway. You can really go to the Google Earth. You can see the spillways being constructed already. This is the spill channel, and while making the spill channel, there were several issues with the Google Earth. This is what you see. Just to give you a feel, this is not the dam. This is only the coffer dam portion I am showing. And gap 2 is the longest portion of the dam, about 1.75 kilometers. So several geotechnical investigations were carried out. The geotechnical investigations were several boreholes were drilled, UDS and samples were collected, SPT tests were conducted. Then we said, see, this is a dam structure. We need a better quality investigations. And I don't trust the SPT tests conducted below the water table. And electric cone penetration tests were conducted. And shear wave velocities are also important, not only for finding whether the soil is going to liquefy or not. When the dam is subjected to an earthquake, how does the dam itself behave and how does the spillways behave? These are the things, and this is also an essential input we required. So this is like a geotechnical engineer's dream, getting all kinds of data at a particular location. To let you know, boreholes at 3 meters offset and CPTs around 10 meters offset from the cutoff wall. I will talk about it in a minute, and they were conducted along the dam axis. Okay, cutoff wall, I will just explain to you in a minute. Also, 2 cross-hole tests were conducted. One test was 63 meter deep, the other one is 93 meter deep. And after 2 tests, one test did not perform well. I'm sure most of you are familiar with the electric cone penetration test. This is a continuous, we push a cone continuously into the ground and we measure few quantities like tip resistance and the sleeve friction, and also we measure the pore water pressure, so that based upon these we can classify the soil. In terms of classification, it is not like the typical classification. It is about soil behavior type. We can find what is the soil behavior is likely to be. Is it going to be like sand-like or silt-like or clay-like? Based upon the trip resistance and sleeve friction and friction ratio, we can get these properties. And this is how, based on a truck, you are going to push a cone down. You can go to about 30 meter or 20 meter depth, depending upon the capacity of this truck and the type of the soil. So when you look at the data, we superimposed the data along the dam axis, and based upon the geotechnical information, a large portion of the dam consists of sand, and another portion contained a clay of high plasticity. Clay of high plasticity. So this is like a geotechnical engineer's dream. Here, liquefaction is an issue, and here, settlement of the dam is an issue. So this is a very interesting case history. And also, when you make a dam on this cross section from upstream to downstream, lot of water would flow down. So when you make a dam on the top and you don't take care of the seepage loss through this, you are going to have a lot of seepage loss through the sand. And tomorrow, Peter Hanjoff is going to talk about, they made a plastic concrete wall, COW, that's what I have written there, cut off wall. What it is cutting off? It is cutting off the plastic, the seepage. It is made using a plastic concrete. And tomorrow, another gentleman will be talking about it to you. So one side you have liquefaction, on the other side you have settlement. This is along the length of the dam. This is the primary cross section. Here, this is all sand portion, and it is a poorly graded sand. And on the left side, that is on the right bank, it is a clay of high plasticity, and it also has some layer of the sand. Now, if you look at the plasticity index of the clay, it is coming about 40%. 30. This is the plasticity index of the clay. And the liquid limit is almost about 60 to 70, as high as 80. And the plastic limit is about 20. And you can see here that natural moisture content of the soil is around plastic limit. It is not less than the plastic limit. It also sort of indicates that soil is sort of normally consolidated. Soil is normally consolidated, which implies that when you construct, you are going to have large deformations. And in fact, these are the consolidation curves carried results of the consolidation curves from Csmrs. You can see this curve like a textbook curve. And I was talking about the presence of high plastic clay. I'm just showing you a small video. This is not a video. I'll just show you, this is a static picture, and you can see here when they are excavating the dump, a lot of earthwork would be involved. They are starting to put it on the top. Okay, now because of this, since this is clay, you can see slippage occurring, slope failures are occurring. You can see here, this is a road, and this pavement, all the stuff has come down, and a severe amount of distress is observed. You can see here very clearly large cracks and downslope movement. This is a small video for you. You can see the failure. Now, why should we do ECPT test? As I told you, electric cone penetration test is a lot more. It gives you a lot of engineering properties can be interpreted it from compared to the SPT, and you can find what is the soil behavior type. So based upon the friction ratio and the cone resistance, I can sort of find whether it is going to behave like a sand, or it is going to behave like a dense sand, or it is going to behave like a clay, without actually conducting any liquid limit or grain size distribution curve or plastic limit test, just by pushing a cone into the ground. So now there was a question and people asked whether the ECPT test was correct or not, or the SPT test was correct or not. Now you can see here, this ECPT 05 and borehole 07, they are very close to each other. And at this location, here you have a clean sand. Below that, you have a clay of high plasticity. Okay. On the left side, if you take a look at it, the ECPT test, without going through a lot of difficulty like SPT test, it is telling you that this is sand and silty sand. And this zone is being classified as clay and silty clay. If you really want to cross check, I think this is the best way to conduct the test next to each other. And these points correspond to this zone, and these points correspond to this zone. So ECPT is a better tool. And this is another borehole which are close in another borehole, and a ECPT which is very close to each other. You can see the N values are 3, 4, 6, 8, 14, 16, 13, almost to a depth of about, it is no more than 20. It started to be more than 20, about 19 meters, I would like to observe. And if you look at the cone resistance also, it is very poor in the top. I will show you in the next diagram. So which shows that the sand there is susceptible to liquefaction. This is another example, and you can pay attention to these SPT N values. About the value is becoming more than 20, typically about a depth of about 13 to 14 meters. Cross hole tests were also conducted just to find the shear wave velocity, because it is also gives you a fundamental property to dynamic analysis, and also you can find the liquefaction susceptibility. At two chain edges, the tests were conducted. One is at 550 meter chain edge to a depth of 63 meters. The other one close about 70 meters apart. Another one is conducted 93 meters apart. And here you can see that when the soil is only about 70 meters apart, okay, 70 meters apart, we expect similar behavior, but there is a large variation in the shear wave velocity, and the test was not conducted properly. And it is very time consuming test, and then we used empirical correlations available in the literature to figure out which test was conducted correctly and the other one is not conducted correctly. And as you can see here, this is the measured shear wave velocity at a chain edge of 550 meters. These are all from the literature. You can see the black line and the blue lines. These are all from the literature. Whereas this red line is well below the literature line. Here, you can see here that the literature, whatever we have estimated and whatever we have measured are in line. These correlations are not based upon one equations. We used several correlations to figure out whether it is correct or wrong. And we can, looking at this diagram, we can say that, okay, I can discard this test. Now to assess the liquefaction susceptibility, the standard procedure or the simplified procedure, or more popularly known as Seed and Idris procedure, has been adopted. Here you need to find two factors. What is the cyclic resistance available at a particular depth when an earthquake occurs, and what is the stress applied. That means it is basically the load applied and the strength available. So factor of safety is resistance to the load applied. Now, how do you decide which parameters do you want to use for the liquefaction analysis? If you get into this, they ask you several things. What is the magnitude of the earthquake? What is the peak ground acceleration? But these two factors usually geotechnical engineers do not come up with. We interact with a seismologist, and based upon the recorded data or the earthquake catalog, they generate either based upon probabilistic analysis or deterministic analysis, what is the maximum earthquake magnitude likely to occur and what is the peak ground acceleration. So the earthquake magnitude given by the Department of Earthquake Engineering, IIT Roorkee, is 6.5. And the peak ground acceleration that is likely to occur at the site is given as 0.16 times gravity, 0.16 g. Now, the resistance to liquefaction susceptibility, the resistance is typically estimated using SPT values or cone penetration test or shear wave velocity measurements Another important factor which decides if the soil is going to liquefy, what kind of ground improvement technique you want to use, is the percentage of fines in the sand. That is, what is the percentage of silt in the sand. As you can see, this diagram represents the average percentage of fines with the depth along the width of the dam. Is average. So from 0 to 3 meters, it is less than 3%. From 3 to 6 meters, 12, again 12 meters, I can say 11 meters, it is all less than 3. At few locations, it is shooting up to 6% or 10%, which indicates that this is a clean sand. If the percentage of fines are more, then the treatment method would be different. It is a clean sand. Insignificant percentage of fines in the entire stretch of the dam. This is how the N values but just for the sake of academic interest and to look at what's going on, the n values were plotted. You can see here up a n value of 20 is reaching about 15 meters. Till then, even at 20 meters depth, there are some n values which are less than 20 and some values which are higher. And at deeper depths, these n values are very low n values were observed. And I believe that is due to the reason that the tests were not conducted properly, rather than sand being at a density corresponding to that level at that depth. So what we used is average n value was used, and factor of safety, that is the cyclic resistance ratio to cyclic stress ratio, we have used as 1.5 because this is a very important structure and several villages will be affected, several hundreds of square kilometers, and a factor of safety of 1.5 is adopted. So this is how the seismic load in the ground will be applied as you go down, and this is the resistance available with depth. We plotted a curve between the ratio of these two. As you can see in the top, the factor of safety is less than 1. That means the applied load is much more than the cyclic strength available for the soil. So when you plot this curve and we took a 1.5 meter, 1.5 as the factor of safety, then the depth of liquefaction is coming around 16 meters. Then we had about 27 CPTs conducted, and analysis is carried out for each individual CPT. Okay. Even now here they said that the committee, there is something called a dam design review panel, and they said that, okay, let's also use here a factor of safety of 1.5, even though it is high repeatability and resolution. And here the factor of safety I calculated for each of them. This is the average factor of safety for the 27 of them. You can see here, even some points are at some locations, they are less than 1. So if you calculate the average of these two and you decide a factor of safety of 1.5, then the depth of liquefaction is coming around 9 meters. And when we conducted based upon the shear wave velocity, we are getting 6 meters at one location and 24 meters at another location. And we really didn't want to get into that because the shear wave velocity itself at the other location became questionable, as explained previously. So finally, it was decided that the depth of liquefaction at the site is decided as 20 meters. In fact, it could have been 16 meters also, but they said it is a dam and a lifeline, and we should not get into trouble. Now, how do I improve a large area of the dam? The width of the dam is about 350 meters or 400 meters. So and the length of the dam is about 1.75 kilometers, of which about 1 kilometer is completely sand. So how do I go about it? It is a very large area, and increasing the density is a big task. So as an engineer, I thought, okay, we can I can convince the authorities that let's do something called explosive compaction, which implies that you are going to embed TNT charge at different depths below the riverbed and then you are going to detonate it, and you are going to cause artificially some excess pore water pressure generation, and then the sand would settle. I think that would have been the most economical and fastest technique, explosive compaction. But I couldn't get my way through the project because they said no, to get the explosives it is very difficult thing, you require the permissions, environmental ministry and police, Naxalites and everything. It got very complicated. Also, not any project has been executed in India to the best of my knowledge using explosive compaction. So we couldn't make a way forward. Then what is the best technique? Here the percentage of fines is almost nil, 3 to 5% or less than 3%. So it is a clean sand, and in the clean sand, if you take a clean sand, loose clean sand in a glass and then you vibrate it, then the volume of the sand is going to decrease in the glass. So your density is going to increase. The technique is, as probably must be been explained by Dr. Ria, and it is known as Vibro Flotation. What we do is we send a vibrator into the ground, and then it is going to vibrate it significantly, and then you retract it. When you are retracting, you are going to put additional material so that the density of the sand here is going to increase. Now, before you undertake, you need to worry about what is the density of the sand in situ and what is the density after I improved using this vibro flotation technique. Because as engineers, you have to pay the contractor. Ultimately, the owner wants to pay the contractor. So there should be a proof of the concept and bill of quantity. So how do you check? Quality assurance was a big issue. So for the quality assurance and to have the confidence, what we did was we carried out trials. Okay, 2 trials were conducted, and ECPT, that is electric cone penetration test, was conducted pre-compaction, that means existing ground, and after conducting the ground improvement, we conducted the post ECPT. Because you need to know what is the improvement in the relative density of the sand after post compaction. And also we want to economize the cost. So we carried out this at 2 meter center to center spacing. Each hole is at 2 meter. If you look at the plan, each hole, each time it is at 2 meter center to center. And the other one is at 2.5 meter center to center. So we carried out the trials. We found what are the pre-ECPTs and what is the post-ECPT, so that we can find what is the improvement. This is all for my record. Now the next question is, how do you estimate the unit weight? People said we would like to know what is the unit weight now, how much it has improved. I kept on telling them that unit weight is not a very good property, and let's get into relative density. But anyway, we started to learn. And so how do you estimate the unit weight? If you go through the literature, ECPT test gives you what is the unit weight of the soil based upon your cone resistance and friction ratio. So what we did is we found the unit weight before the compaction was carried out. And you can see here, this is varying between 16 to 17 kilonewton per cubic meter. In the other case, in the another site, it is around almost 16 to 17 again. Okay, so we did quite a bit of ECPTs and we found what is the depth, what is the average unit weight, and post improvement after the execution was carried out, what is the value of the unit weight. So from previous to now, it has gone from 17 to 18 to it went to 18 to 20. You can easily see that now the unit weight of the in situ sand has increased. Is before ground improvement. This is after ground improvement. So you have to check this now. Every time you have to pay the contractor. So you have to do a pre-ECPT. This is the quality assurance scheme. And then you have to do post ECPT. You cannot do SPT here because it won't be very reliable. So you have to do post CPT to carry out the payment. If it is less, then you have to repeat the process. Now, we also found what is the relative density. I believe relative density is a better parameter to decide whether the sand is in what kind of state instead of your unit weight. So, in situ ground, as you can see here, it is about 60% relative density. The contract specified that the relative density post compaction should be about 90% or above. This is the relative density before the compaction work is about 60%, as you can see here, the dark black line. Now the contractor engineer in charge said that it should go to 90% or above for payment to be made. Okay. In some cases, it went up to 85, 90. Getting 95 relative density or 100% relative density is not possible in sand. People say that we can achieve, but you really cannot get it. Now, if you go back to the literature, relative density from the CPT, there are several correlations. This is your pre and post. This is pre and post. You can clearly see that there is a marked increase in the relative density, but reaching to 90% was very difficult. So then we also carried out a technical study. Why did the engineer in charge select this? Now, we said, if you start working like this, then you are going to be in a lot of trouble. So we said that let us use how many correlations are available in the literature for finding the relative density. For example, Schmettmann's is one, Baldi is another one, Willett and Mitchell chart. So we said, okay, each time calculating the relative density using the spreadsheets in the field is very difficult. So we told them, let's see what tip resistance do you require to pass the bill. Ultimately, that is the criteria, isn't it? As most of you are engineers in charge, so they will ask you to pass the bill. Where is the quality control? So we arrived at what is the minimum QC required for paying the bill. Okay, this is the range of QC required for 80 to 90% as per Schmettmann's curve. See, all these things are well above, isn't it? It is falling well above. Now, for 80% and above, this is the curve. This is using another correlation, Baldi, and this is the QC required for 80 to 90%. You can see that this red line is well above this band of 80 to 90% required. Then they said, okay, you are all using, Professor Ramana is using all the old correlations. They said, let's use the latest correlation. When we started using Kohlhavy and Main, that is very recent one, like 30 years old, in that case, the QC required is slightly higher compared to all the three correlations available. And in fact, in some cases, the QC is less than the QC required to pay the bill. Then we had a lot of arguments and we debated about a long time, and we reached a consensus that whenever we took the average of these four, because there are four correlations and we can't stick to one correlation because all these correlations are empirical. So empirical things require judgment. So finally, we decided that we will use the average of these four correlations, and whenever the QC is above the average of these four, we are going to pay the contractor. And just to show you, this is the Vibro compaction work in progress. This is the vibrator that is going down into the ground. You go down and then start compact. Once you reach the required depth, then you are going to vibrate it, and then you are going to put the sand. When you carry out at this location, at this location, at this location, like predetermined positions, after you carry out the work, you can see the subsidence of the soil. The soil went down by 5 to 7% of the 20-meter height, which clearly shows that the soil has attained a higher relative density. This video shows how it is going down into the ground. While it is coming up, it is vibrated at different depths till the current required to move at the sand is being filled into the dip. So Vibro compaction works and observations and recommendations, and I think ECPT is the best method to record the continuous monitoring of the resistance of the ground to verify pre and post engineering behavior. Of course, there is a lot of debate in the literature, and some people say that this is not a very reliable method, but this seems to be very good. And at the Polavaram project site, the fines content were less than 5%, and an average post relative density of 80% was achieved. Okay, if your post relative density more than 80% is obtained, then you don't have to worry about the liquefaction hazard, as well as it will improve the bearing capacity and reduce the settlement. Also, I think I'm sure this must have been shown by somebody. And in this presentation, Professor B. Janakiramaya is at IIT Tirupati. He helped me out. And Mr. Skeller, Mr. Mohammad Rafi, he is associated with the project for about almost a decade or so, or 8 years or 6 years. And several contractors changed, but Mr. Mohammad Rafi is constant. and Dam Design Review Panel for giving this opportunity to work. And I will, this is the best I can show you. I will just show you a small video right now for another small failure. Just a second, please. There was a small video where we had not the flood photos. In fact, I was talking about the clay, and this was I was watching it last year. In place. You can sleep here. This is not to do with the sand, and this has to do with the loading on the top of the waste material. They started to store on the top, and we told them that you should not do that, but they didn't listen initially. So that's what it is. I'll be happy to take a few queries.
Thank you, sir, for making an excellent and detailed presentation. May I now request to the participant, if they have any questions, they may ask.
I'll be happy to take if I can.
Thank you, sir.
Thank you very much.
Thank you very much.
Thank you.
If the still participant have any questions, they may write to us. We will arrange the answer from the speaker and get back to you over the email. Or if they still want to ask directly to the speaker, they may.
Great, madam. So thank you, everyone. It was a pleasure seeing you, some of you virtually. And thank you, CBRP, for giving me this opportunity. Thank you, ma'am.
Thank you, Dr. G.V. Ramana, for sparing your valuable time and conducting this virtual session. Thank you so much. See you all tomorrow at 1100 hours. Thank you all for the day and your time. Stay safe, stay healthy. Thank you.